Welcome to the deep dive. We're here to take complex academic stuff, pull out the key ideas, and basically give you the quick version so you're up to speed. Today, we're getting into something really core to, well, almost any kind of quantitative thinking. The material we're using, it's from a university course. Looks like Econ 125 MTA, covering statistics and business decision making.
Yeah, and the lecturer pointed something out right away. Statistics, it's huge. You couldn't possibly cover it all, not even in a full year.
Yeah.
So they kind of bypassed all the complexity.
Right. They decided to zero in on what they called the most far-reaching and vastly used aspect.
Which boils down to probabilities, how to develop them, how to analyze them.
It sounds simple, but this is the stuff behind, assessing risk, figuring out what customers might do, even making big money business choices.
Exactly. So our goal today, just follow their lead. We're going to break down the absolute basics you need to build a simple probability. Think of it as like the ABCs for anyone working with data or trying to figure out odds.
Okay, let's start right at the beginning then. We all say things like, it'll probably rain or I'll probably be late. But what does probability actually mean in this stricter academic sense?
Well, the notes keep it pretty straightforward. It's defined as simply the chances of something happening.
Okay.
But that simple definition comes with probably the single most important rule in all of probability, like the absolute foundation.
And that is?
A probability is always a number between 0 and 1, period. It can also be 0%, meaning impossible, or 100%, meaning it's a sure thing.
Ah, okay.
But it can never be less than 0 or more than 1. So if you're calculating chances and you get, 1.2 or negative 0.5,
You messed up somewhere.
you're definitely messed up somewhere. That's your immediate red flag. It's a hard limit.
That's actually really clear. But hang on, let me just push on that a bit. Because you hear things all the time, like in business news, about 200% growth or maybe 150% return on investment. How does that fit? Are they just using the word wrong?
That's a great question, and it's a really important difference, that 0 to 1 rule. That's strictly for the probability, the likelihood, of a single event happening.
Okay.
When you hear about 200% growth or 150% return, those aren't probabilities. They're measuring a change or an increase compared to a starting point.
Ah, got it. Different concept.
Exactly. So you can have sales that are 150% higher than last year, but you can't have a 150% chance of closing a specific deal tomorrow. Two different things.
Okay, that makes sense. Clears up the boundaries. So staying within that 0 to 1 range, the source says there are 3 ways we can write down a probability.
Yep, basically 3 interchangeable formats. You can use a fraction, like 1/2,
12.
or a decimal, like 0.50,
Like that.
or a percentage, 50%.
Yeah.
They all mean the same thing. Usually, when you get into more complex calculations, the decimal format is maybe a bit easier to work with. But fundamentally, they're all just different ways to say the same chance.
Perfect. Okay, limits established, formats clear. Now, how do we actually calculate this number? The source materials seem to stress there are 2 really different ways to approach this. The first one is about looking at what's already happened.
That's the one. The notes call it the empirical approach. You might also hear it called the relative frequency approach. The key word is empirical.
Meaning?
It means it comes from observation, from experience, from data you've collected.
Yeah.
You use this approach when you already have information about how often something occurred in the past. You've got a track record.
Track record, I like that. Like a history book of results.
Yeah.
So the formula has to be based on that history, right? Not just theory.
Exactly. So if you want the probability of some event, let's call it event A or PA,
P-Babe.
you figure it out by taking the number of times event A actually did happen in your observations,
Okay.
and dividing that by the total number of times you looked, or the total number of simple events in your experiment. It's basically successes divided by total observations.
Let's ground that with the Nike example they gave. So Nike researchers go out, they survey 1,000 random people. That 1,000, that's our total number of observations, right? Our goal.
Right, that's your denominator. And then they observed that 900 out of those 1,000 people recognized the Nike swoosh logo. That 900 is the number of times the event recognizing the logo did happen,
So simple division. P, recognized logo, is 900 over 1,000.
which is 0.9.
Or 90%. And that 90% isn't just a number, is it? It tells Nike something really important.
Oh, absolutely. It's huge. A 90% recognition rate. That means they can pour money into advertising a new shoe, for example, without having to spend much time explaining who Nike is. People already know.
Yeah.
But imagine if that number was, say, 10%. Their whole marketing game would have to change completely. They'd have to build brand awareness first. So this empirical approach, it's powerful because it's tied to reality, what people actually did or knew.
Okay, that's super clear. Empirical means looking back, based on observation. But then there's the big what if. What if you don't have that history? Like you're launching a totally new product, you have zero sales data. What
Right.
then?
Then you shift gears. You move to the second method, described in the notes, the classical approach.
Tricycle.
Okay,
Okay.
this is the one you use when you're more in a theoretical space, you don't have historical data, but you do know something fundamental about the possible outcomes of the event.
And there's a huge condition attached to this one, isn't there? The source really emphasizes this.
Crucial condition. You can only use the classical approach if you know for sure that every possible outcome has an equal chance of happening.
Equal chance. That's the key phrase.
Absolutely. If the outcomes aren't equally likely, the classical approach just doesn't work. It falls apart. It needs that perfect balance, that symmetry.
Okay, so if you have that perfect symmetry, if every outcome is equally likely, how does the calculation change? It can't be based on what did happen anymore.
Right. It shifts from history to potential. The formula becomes
Yeah.
the number of ways your event can happen,
Okay, can it happen?
divided by the total number of possible outcomes.
Yeah.
You're not looking back, you're looking at the theoretical structure of the event itself.
And the classic example is always the coin flip, right? Like
Yeah.
the one in the notes.
Yep. What's the probability of flipping a standard coin and getting heads?
Well, there's only one way for heads to happen.
That's your numerator.
One. And there are two total possible outcomes. Heads or tails, assuming it can't land on its edge.
Right. Assuming a standard flip. So that's your denominator too.
So P heads is 1 over 2.
Or 0.50 or 50%. See, we didn't need to actually flip a coin hundreds of times and record the results. We used our knowledge about the coin, that it's fair, balanced, two sides, to calculate the probability theoretically.
But doesn't that just point out the big weakness here? We're assuming it's a perfect coin. We're assuming a standard die is perfectly weighted. What about loaded dice? Or a bent coin? Doesn't a real world kind of mess up the classical approach?
You've hit the nail on the head. That's precisely the tension. The classical approach is great, it's clean, it's often easy to calculate if the assumptions hold.
If. Big if.
Huge if. If you even suspect the coin might be biased, or the die isn't fair, meaning if you suspect the outcomes are not equally likely, then the classical approach is the wrong tool. You have to abandon it.
And go back to the empirical method.
Exactly. You'd have to actually run an experiment, flip that suspect coin many times, record the results, and then calculate the probability based on what you observed. That gap between the clean theory of classical and the often messy reality that demands empirical data, that's like the heart of doing statistics properly.
Okay, so let me try to summarize the difference then. Empirical is looking back, using actual observed data, history, it's retrospective.
Yeah.
Classical is looking forward, based on theory, assuming all outcomes are equally possible. It's prospective, but with a big asterisk.
Perfect summary. Now let's see if we can apply that. The notes had 4 practice problems. For you listening, don't worry about doing the math right now. Just think. Which approach, empirical or classical, does each problem need?
All right, problem 1. A survey finds 5 out of 50 Mercy College students liked statistics. What's the probability a randomly chosen student from that group does not like statistics?
Okay, what's the trigger word there?
Survey.
Bingo. Survey means data was collected. We have observations of what did happen in that specific group of 50, so it has to be.
Empirical, you'd calculate 45 divided by 50, based on the actual results.
Exactly. Pure empirical. Okay, problem 2. Probability of rolling a 2 on a single roll of a standard die.
Standard die implies fair, right? 6 sides, each equally likely. We don't need to roll it first.
Right. We know the possible outcomes, 1, 2, 3, 4, 5, 6, and we assumed equal chances.
So that's classical. One way for a 2 to happen, 6 total possibilities. 16.
Perfect. Classical it is. Problem 3. Probability of guessing the correct answer on a true or false question.
Okay, similar logic. 2 options. True, false. Unless you have some inside info, you assume each is equally likely for a random guess.
Right. You know the structure. 1 correct answer, 2 total options.
So classical again, 1 out of 2.
Nailed it. Now the last one, problem 4. What's the probability of picking a Mercy student at random and finding out they're a senior?
Ooh, this one feels different. My first thought might be, well, there are 4 classes, freshman, sophomore, junior, senior, so maybe it's 1 out of 4. Classical.
Ah, but is it equally likely that a randomly chosen student will belong to any one of those 4 classes?
Probably not, right? Colleges usually have more freshmen than seniors due to dropouts or transfers.
Yeah.
The numbers aren't perfectly even.
Exactly. That assumption of equal likelihood, that 25% chance for each class, That's using the classical approach where it likely doesn't apply. It's almost certainly wrong.
So you can't use classical. You'd need...
You'd need the actual data. You'd have to look up Mercy College's current enrollment numbers, find out how many seniors actually are enrolled, and divide that by the total number of students enrolled overall.
So you need the real numbers, the observation. It has to be empirical.
Precisely. That one really shows the limits of the classical approach in many real-world situations. Assuming equal likelihood can lead you way off track if that assumption isn't justified.
Okay, this is starting to really click. So wrapping up the core ideas here for everyone listening, we've got the absolute rule probability lives between 0 and 1 always.
Non-negotiable.
And then 2 main doors to calculating it. Door number 1, empirical. Look back at the data, see what actually happened, use the history book.
Right. Observations rule.
Door number 2, classical. Look forward based on theory, but only if you're absolutely certain every possible outcome has the same chance. Think fair coins, perfect dice.
The idealized world scenario. Knowing which door to open based on the situation is step 1.
It determines if your answer is based on reality or on a theoretical model.
And that distinction is everything.
Okay, so the source material actually stops right about there. The instructor apparently planned to get into more feedback and discussion on these ideas next time, which leaves us with a great final thought to ponder.
Yeah.
We talked about the clean world of classical probability, perfect coins, fair dice, and the messy real world where empirical data seems needed more often. So the question for you to think about is, outside of actual games of chance, how often in the real complex world can we truly be confident enough to use the classical approach?
How often are things really equally likely when it comes to business or people or nature?
Or is almost everything we try to predict or analyze ultimately driven by the kind of messy historical patterns that demand we roll up our sleeves and use the empirical method?
It's a great question. That space between the neat theory and the complicated reality. That's where the real work and maybe the real insights happen.
Definitely something to chew on. We'll leave it there for this deep dive.